is Basic Theory T104. So in this video we're going to be looking at Boolean algebra, specifically how to simplify some of these expressions that we've been given. So let's look at this expression here, A or B and not A or C. We're going to see how we can simplify this expression, and on the next slide I'll go into what these operators mean. But here's what you can call them by name. The dot represents the logical product, the plus sign represents the logical sum, and the bar above any expression represents the negation of that expression. So here this just represents the negation of B, whereas this line on the top represents the negation of the whole section. So before we try and tackle the problem, let's just quickly go over some of the basics of Boolean algebra. It was invented by an English mathematician called George Boole, and all it really does is convert verbal logic into algebra. So rather than using the word and, we've got these algebraic symbols that we can perform some mathematical functions on, and that makes it very useful for minimizing circuits and other sorts of techniques. So let's now look at De Morgan's theorem, and it's one of the most important digital design tools when looking at digital circuitry, and it helps with logic minimization. And basically what we're doing is, in this instance, we're converting from an AND to an OR gate, and in this instance we're converting from an OR gate to an AND gate. So what we're going to do is we're going to apply these theorems with our expression here, and I'm going to do it on the next page just so you can see the workings. So let's start by recalling the problem on the previous slide. So we've got A or not B and not A or C. So what we can do is we can kind of see that we could replace these whole two terms with different variables. So let's call this E and let's call this F. So if I then write this up over here, we've got E and F inverted. And from De Morgan's theorem on the previous slide, we could say that this was equal to not A or not B. So let's apply this to this term over here and see what the outcome is. So this is going to equal A or not B, because this is still our E term, but this is all going to be inverted or negated. And then we can say, rather than the AND in between, because we've applied De Morgan's theorem, we're going to have the OR in between. So this is going to be OR, not A, or C. And again, this is going to be inverted. So what we can see again is that we're going to be applying De Morgan's theorem, because we've got this whole negated term or inverted term. So here our A and our B are going to equal, let's call them E and F again just for consistency, equal to E, equal to F, and here equal to, let's say, G, and here equal to H. So if we go up here and apply De Morgan's theorem, this time we've got E or F, all inverted. Well, this looks like De Morgan's second theorem, and this can be equated to not E and not B. Not F. So what we can do is we can apply that to this one, and similarly for the G and H terms, G or H, all inverted, is equivalent to G inverted and F inverted. So let's apply this on the left hand side. This will become A inverted and B inverted. But you've got to make sure here, this is quite a small trick that you might miss sometimes. This has already been inverted once, so we've got to make sure that we invert it twice here, and we'll come to how this can simplify in just a minute. This will then be ORed with our A inverted twice, ANDed with our C inverted once. So what can we do to simplify this? Well, here all we can see here is that our B is going to be inverted and then inverted again, and that's just the equivalent of not inverting it at all. So I'll just write that over here. A not is equal to A. So we can apply this to our term over here, and our final outcome is going to be not A and B, or A and not C. So let's compare that with our answers from the question. So if we followed the same steps as we did on the previous slide, this is the same workings but slightly neater. but without the explanations, we can see that we came to the same conclusion down here. So that this was our answer, and this corresponds to the answer A. And so, as we said, the answer is A. And let's just recap what we've gone through here. We've gone through the reasons why we use Boolean algebra, Boolean algebra itself and how it kind of works, and also De Morgan's theorem and how we can use that to simplify expressions to create more readable logic.